Hello everyone, you are feeling fine? Okay, let's resume our class of soil mechanics. As usual, if you need a French version of this video, you can find a link in the comment, okay? So, in today's video, we will continue our chapter 2, which is origin of soil and grain size, okay? In this video, we'll talk about mechanical analysis of soil, which is the 7th section of this chapter. So from section 1 to section 6, we have talked about in previous videos. So in this video, the second video of this chapter, we'll talk about mechanical analysis of soil. And next time, the next video, we will talk about these two last part. Okay, so let's go. Mechanical analysis of soil. What is mechanical analysis of soil exactly? So this mechanical analysis of soil means determining the size range of soil particle. Size range of soil particle by expressing this with a percentage of total dry weight of the soil. Generally, two methods are used for this: sieve analysis and hydrometer analysis. What is sieve analysis? Sieve is just sieve, same we are using in our kitchens. So this is sieves are used to sieve soil. And for this sieve analysis, they are used for soil particle larger than 0.075 millimeter in diameter. Okay, so it involves passing the soil through a series of sieves. And these sieves are, when you're going down, they are getting smaller. I mean, the opening of the sieves are smaller when you are going down. Yeah, so you just place your soil sample on the top and you shake the sieves so that the soil pass through the sieve. Okay, and then we measure the weight of soil retained on each sieve. Then the result are used to calculate the percentage of soil particle within specific size range. How about the hydrometer? Now we are talking about this sieve analysis and hydrometer analysis, just roughly speaking, not in detail. So after that, we will talk about them in detail also. So what is hydrometer analysis? Hydrometer analysis is, this is what I'm doing here. This is me when I was a bachelor's student in my country. So this analysis is used for soil particles smaller than 0.0975 millimeter in diameter. So it involves dispersing the soil sample in water. So you mix that soil sample in water and to create a suspension by mixing the soil, because the diameter, the soil particle are very small, 0.075, it's small. So you can mix it with water and it will be like a suspension. And then we use a hydrometer to measure the settling rate of the soil particle, because after mixing this soil particle in the water, this particle will settle down. They will shrink. So the settling rate, I mean the velocity, the speed of settling will provide us information to know the particle size distribution. Okay, so these two methods means sieve analysis and hydrometer analysis. They provide us good information to make the particle size distribution of the soil. So sieve analysis for particle larger than 0.075 and hydrometer analysis for soil particle smaller than 0.075 diameter. And we combine them together, it will give us size distribution, particle size distribution of the soil. And this particle size distribution is widely used in geotechnical engineering and soil science. Okay, now let's talk in detail about the sieve analysis. Okay, how it works exactly. We know that we have to put our soil sample on a stack of sieves and shake them. But how it works exactly? So remember that this is for particle larger than 0.075 millimeter in diameter. Okay, so to perform this analysis, the soil is subjected to shaking through a series of sieves, progressively smaller in opening. It means, I explained already, the opening, as you see this one, the top sieve, the top sieve is it has the largest opening. So as you go deeper, the opening size decreases. So, for example, if you take the US standard sieve, the the sieve number, because this sieve, they have number. Okay. From the top one to the bottom one, they have number. So for the US one, this table is showing the sieve number and the opening, the size, the opening, the size of the opening. Starting with the sieve number 4, which has opening 4.75 millimeter, to sieve number 270 with opening 0.053. If you're wondering how this number is the number of sieves are given, it's simple, because some people will ask why start with 4? Why not start with number 1, 2, 3, 4? Actually, these numbers are given according to the number of opening in 1 inch. Okay, 1 inch square inch actually. So if you go, if you measure in 1 inch square inch, how many opening you have? So this, for example, sieve number 4, it means in 1 inch, you will have four openings. Okay, in 1 square inch, you will have 4 openings. That's why the sieve number is 4. And all of them are like this. And just for comparison, remember I said for sieve analysis, the size is in diameter larger than 0.075. And hydrometer, analysis, size smaller than 0.075. So actually, the soil we take to make the hydrometer analysis is the soil obtained in this sieve number 200. Okay, so we can take this, but for good analysis, hydrometer analysis, people are taking this one around 0.050. It gives better result. So anyway, the soil we use to make hydrometer analysis is obtained from this sieve analysis. So after completing the sieve analysis, you take the soil at the bottom, the last, or I don't know, the first, depending from where you start, the bottom sieve or the pen. The soil containing in that sieve has smaller particle size. So we take that one to make the hydrometer analysis. Just for comparison, this is American, the US standard, and this one, right one, in this table is French standard. Just corresponding, there is we can make a correspondence between the two. For example, sieve number 4, Tami means in French, sieve, is corresponding to a modulus 38 in French standard. And this one, American Society for Testing and Material, maybe you know already, but this one, AFNOR, means Association Française de Normalisation. Yeah, like French Association for Normalization, which is the meaning. So I think in Japan, this one, American one, is used. Yeah. So typically, the sieves they use, they have diameter of 203 millimeter, like this diameter. And before conducting this analysis, sieve analysis, the sample need to be dried, oven dried, and some slump. If there are any slump, they should be broken in small particles. So the soil is then shaken through the stack of sieves, and there is a pan at the bottom to collect all the particles beneath. So after shaking the soil, we can then determine the mass of soil retained in each sieve. Okay, so the portion of the soil retained in on each sieve is then collected separately, and we dry them oven dry, and we can weight them to know the mass of each soil portion retained on each sieve. And what we do with that, we'll explain later how we use that, the mass retained on each sieve. Just in case of a cohesive soil that are sometimes difficult to break in individual particles, we sometimes mix the soil with water to make it like slurry, which then we wash the slurry through the sieves. I have never done that one. This one I did many times, but using water and washing like through the sieves, I have never done that. Okay, how it works exactly? Let's explain step by step how it works exactly. Step number one, after shaking everything, and now some people use machine to shake the sieves, but some people do it just manually because they don't have enough money to buy machine to shake the sieves. So after shaking, and then you have on each sieve a part of your initial soil sample. Then you can determine the mass by weighting each part on each sieve. Okay, so we measure we weight and get the mass of soil retained on each sieve. For example, sieve number, let's say 1, but of course this is not about the opening, the true number of sieve. Let's say M1, M2, up to Mn. And the pen at the bottom, which is at the end, we call it MP. So after that, the next step is we can obtain the total mass. Of course, we had the total mass also. If you want, you can weigh the total mass of your soil sample at the beginning, before even dropping it on the top of the sieve. So by weighting each soil retained on each sieve, we can sum them. By additioning all of them, we can get the total mass of our soil sample like this. Okay. Next step, number 3, we can then determine the cumulative mass of soil retained above each sieve. For example, the top one, that one is easy because there is nothing above it. So the cumulative soil and the cumulative mass is just the mass on it that is weighted. But if we take, for example, one sieve in the middle of the sieves, so it means that all the sieves above that one retaining soil particle that cannot go through the middle one. So we cumulate, we add all of them to get cumulative mass of the soil. For example, if we take the ith sieve, so we have to do M1 plus M2 up to Mi to obtain the cumulative mass of that sieve. Okay, that means because the ith sieve has smaller opening, the opening of the ith sieve are smaller than all the sieves above it. That means all the particle retained on the above sieves cannot, of course, go through the ith sieve. Okay, so we accumulate everything, and after that, number 4 is we can then estimate the mass of soil passing through the ith sieve. How can we do that? It's very simple, because we know the total mass. The total is this one, sigma m, by additioning all the masses, minus the cumulative mass. So it is like you take the total mass and you deduct from that total mass all the mass above the sieve. It means the result you will get is the mass that went through the sieve, the ice sieve, something like that. So by doing that, we can get the mass of soil passing through each sieve by using this formula. Then at the fifth step, we can calculate the percentage of the soil passing through each sieve, because this is our target actually. The target is to determine the percentage of soil passing through each sieve. Yeah. For example, if you want the soil, the mass passing through the top one, top sieve, you will do the total mass minus only this mass, the mass on this sieve. Okay. Then the total mass minus the mass above the sieve, all the mass above this. In that case, you can get the mass that went through the sieve. And we calculate the percentage by doing the mass that went through the sieve divided by the total mass and multiplying by 100. This formula is just this one, okay? The mass of soil passing the sieve divided by the total mass, and then you multiply by 100 to get it in percentage. Then this last step is very important somehow, because we will use the percentage of passing to draw a curve. So once the percentage of fine for each sieve, fine here, I mean the finer, percentage finer, mean the percentage of soil passing sieve is calculated as on the step number 5, previous slide. Then we can use it to plot a semi-logarithmic graph with percentage of finer as on the x, the y-axis ordinate. That one is in arithmetic scale. And then the sieve opening, the opening size, we place it on the x-axis, which should be logarithmic scale. So that's why it's semi-logarithmic. Y is normal arithmetic scale, and the x-axis is logarithmic scale. It will give us something like this. Sorry, this graph is in French actually, but the objective here is to show you how the curve will look like. And these are for many soil. Soil A, soil B, pink one, soil C, soil D, soil E. It means this curve should be same for same soil. Okay. If you have a, let's say, a truck that drop soil on your construction site, for example, if you take soil sample from that soil, each soil sample you take from that soil should give you same curve. So this curve are telling us a lot about the soil actually. And next time we will talk about how to use this curve to get soil behavior. For example, how we can use this curve. We can use this curve to get a lot of information about the soil, about uniformity of the soil, a lot of information. It can tell us if the soil is stable or not stable. We will talk about this in future. So, and here we can even see, for example, gravel and sand, depending on this one is the French norm, but if it was American norm, because the x-axis is the opening. So according to the opening, as we talked before, depending on the size, the diameter, there are a lot of classification. So on this curve, we can also, this graph, we can make classification. We can know, for example, here is gravel and sand, and this one is clay and silt clay. So this curve can tell us, for example, if this soil E, as you can see, it's mainly very fine grain. No sand and gravel in this one, this particular soil A. On the other hand, if you see soil A, this one I was talking about soil E, soil A, you see we have sand and gravel in very important portion, and only a little amount of fine soil in this soil. So we can get a lot of information from this graph. Okay. So I think this is this plot, this graph, we call it a particle size distribution curve in soil mechanics and geotechnics. Geotechnics and soil mechanics, we call this curve particle size distribution curve. So I think this is the end of the Sieve analysis. Let's talk now in detail about the hydrometer analysis. And remember, this one is done for soil particles smaller than 0.09075 millimeter. Okay, so how this works exactly? So this is conducted based on the principle of sedimentation of soil grain in water. It means if you put soil in water, soil grain, they will settle, they will shrink in the water, and different diameter mean different weight will shrink differently. The speed of shrinking will not be same. So this is the photo I have explained before. Exactly what I'm just mixing here, the soil sample and water, and after that the soil particle will be like shrinking in the water, sedimentation. So when the soil specimen is dispersed in water, the particles settle at different velocity. So depending on the weight of each particle, they will not settle at same speed. So the settlement speed, settlement velocity is influenced by the shape of the particle, size, weight, and viscosity of the water. To make it very simple, we consider that all soil particles are spherical shape. And the settling velocity can be calculated using the Stokes law. Okay, this Stokes law is this equation number 1, which relates the settling velocity of soil particle to the size of the soil particle and viscosity of fluid. Fluid here is just water. And then the difference between the density of the soil particle and density of water. This is the formula. Okay, let me put this formula up here because we will use it. So if you have this formula now, velocity, this means the speed with which the soil particle will be going down. Okay, so if a soil particle is here, what is the settling speed from the top to the bottom? So if you leave two particles, they with different size, different mass, different weight, they will not go settle down with the same speed. So this speed, velocity, is obtained by using this formula. So weight, the density of the soil particle, density of water, and this is viscosity of the water. D is diameter of the soil particle. So from this, we can calculate the diameter of soil particle. By using this square root, we can calculate like this. And remember, velocity is just distance divided by time. So the distance the particle will go from top to the bottom in the tube, né? And the time it will take from a given position, that will be the velocity, like average velocity. So we just replace this V by L divided by T. So this is the velocity. So remember, in the previous videos, we have talked about specific gravity, this one, GS. So specific gravity is just like ratio. Specific gravity of soil is ratio of the gravity of weight of the soil divided by weight of water. That's the meaning. This is specific gravity. So from that formula, we can say that the density of the soil particle are just specific gravity multiplied by the density of water. And then we can replace this in here, in this density of the particle. Okay, if we do that, we can rewrite this formula to this one, equation number 4. Okay, just replace this this one by this, then we can make it something like this. Then if we use now the unit, the diameter, we want it in millimeter, because the first viscosity will be gram second per square centimeter. And this one also, the density of water, gram per centimeter, per cubic centimeter. And L, distance in centimeter, time is in minute but we want it in second, because here we have second here. We have to convert the time in second. And if we calculate diameter in this, using this, we will have our diameter in centimeter. So to convert this diameter in centimeter, we have to divide it by 10 to convert it in millimeter, because we want diameter in millimeter. And then if you arrange everything, you will get this formula. D equal this one, all this. And by considering that the density of water is about 1 gram per cubic centimeter, so we can replace this by 1, this density of water by 1. So we'll get something like this, with K is equal to this. Because this one will become 1, we will get 30 by viscosity of water and divided by only this specific gravity minus 1. This is the K, actually. This is the K. So K multiplied by square root of L divided by T. L being in centimeter and T in minute. Because we made all the conversion here. So we will get our D in millimeter. So what we need is to get this K, to get the L, and to get the T. So everything is now summarized here. We just need these 3 parameters to obtain the diameter of the soil particle. Okay, I put this formula here because we'll use it again. This one, the specific gravity and the viscosity of the water, of the liquid, depend on temperature of the test. So you should know at which temperature you are conducting your experiment, your test. So this table is giving value of K for each temperature you measure. And also this gravity, specific gravity. So these are specific gravity. For example, if you have specific gravity of 2.65 and you have temperature around 25, so you can read something like this. This is the value of K in that case. Specific gravity of 2.65 and temperature of 25. So now, how do you get the value of specific gravity? That is the hydrometer will give you that by reading the hydrometer. We will talk about this next, in the next slide, how you obtain this. Then, if you obtain the value of K from this table, you just then need L and T to obtain the diameter of your particle. So in the laboratory, for example, people are using this hydrometer test. They take just 50 grams of the soil sample. They dry it in the oven, and they are using a cylinder, sedimentation cylinder. But sometimes it happens that the people take 100 grams of the sample instead of 50 grams. So it means that this is this tube. This tube is the cylinder, sedimentation cylinder. What I'm talking about. So this cylinder, this tube, is about 400 for American standard. I'm talking 457 millimeter in height and 63.5 millimeter in diameter. So it marked for a volume of 1000 milliliter. So means it's just 1 liter. The marker, you can see the mark for 1 liter or 1000 milliliter. So this means the total volume should be 1000 milliliter. So what we do sometimes is to add this sodium as agent to dispersing agent in the water. So after mixing the soil with water, we can add this agent to disperse the soil. So after then mixing the soil with the water, because the volume of this cylinder is 1 liter, so we should complete the volume of our extract, the mixer with soil and water. We should complete with water to make it 1 liter, because maybe after mixing you will not have exactly 1 liter. It's only 50 grams. 50 grams you mix with water. After mixing, maybe it will not be 1 liter. So you have to add more water sometime to reach the marked place of the cylinder. And then after that, you can start doing your test. Then when the hydrometer is placed in suspension, means the mixer with soil and water, like this. This is, for example, this figure is showing this hydrometer in the water, in the mixer, in the extract. At a given time t, it will measure. The time is measured from the beginning of the test. Okay, we start like chronometer, and we start measuring the time from the beginning of the test. After putting the hydrometer, we start measuring. So it will measure a specific gravity in the vicinity of its bulb at a depth L. So you see L here, and this will be, it will give us the specific gravity around here. That means the specific gravity is not same when you are going in the tube. So this hydrometer will give us specific gravity around here, around this point. The depth is L. So the thing is, if you measure here, specific gravity here, at time t, soil particle in suspension at this depth, at this level, they will have a diameter smaller than d, than the d we calculate here. Why? Because large particle, they would have gone down below that part, because they are heavier. So they will go down, they will be down. So what you will have here, the specific gravity you will measure here, will be then smaller than this d you have. So if in that case, it means that this hydrometer is giving the amount of soil that is still in suspension. The amount of soil in suspension, not the amount of soil that have settled down. That is the meaning. So this hydrometer are calibrated to give specific gravity of like is 2.65. So if your soil have different specific gravity, you must correct this. There are possible many ways. So depending on the specific gravity of your soil of your soil, we have some time to correct this because the hydrometer is designed only for this specific gravity of 2.65. So here is if you know now the amount of soil in suspension, the L, if you know, because the hydrometer will give us at a given time t, we can then calculate the percentage of soil by weight finer than a given diameter. Because when we measure here, it means that the soil particle higher than that, and the diameter measured at this time t, they are already down. We can say with confidence that the soil in suspension have diameter smaller than the d with this time. If we take, for example, 5 minutes and we calculate, we know the L at 5 minutes and we know time 5 minutes, and we calculate the corresponding diameter. So it means that at time 5 minutes, the soil that is in suspension, that soil is smaller than have the soil particle smaller than the diameter we have calculated. So we can say with confidence that this amount of soil in suspension is having a soil particle smaller than this diameter. So if we convert it like in the case of sieve analysis, we can say that this amount of soil is passing this sieve number X, for example. So because we are searching for the percentage of soil smaller than certain level, certain range. That is our target. So at that time t, we can say that the soil particle in suspension, because the hydrometer is giving only the mass of the soil in suspension. So we can say in that case, all the soil in suspension, the particle of the soil in suspension have diameter smaller than this diameter d we will calculate at that given time. So the value of L will change with time, of course. And the hydrometer analysis is effective for separating soil fraction down to size of about 0.5 millimeter. For the T, the time, how can we obtain the time? That is simple. We just use a chronometer. Your watch, you can use to measure the time. And this take actually very long time, sometimes overnight. You cannot do it, this test only on one day sometimes. You have to come back the next day to do it, to continue doing it. So this one is obtained easily. Once you start this test, you start at the same time chronometer, checking the time. You start the chronometer. And now, how can we get the L, the value of L? Because if we have T and we have L, remember the K we had it in the table. This value, variation of L, is given in this table depending on the reading of the hydrometer. So each reading, here is hydrometer reading R and L in centimeter. So each reading of the hydrometer, depending on the value of the reading, you can determine the value of L, this L. All our problem is L. Of course, there is a mathematical formula to estimate this L, but maybe these values are given here. So you can just choose this value. After reading the hydrometer, you come and check your reading here or here, and you can determine the corresponding value of L. This is the figure, still continuing, the same figure, continue. Okay, same figure. Yeah. So briefly, let me re-explain again how you do the hydrometer analysis. You will read, the hydrometer will give you the specific gravity. You're reading, and you read, you see graduation on this hydrometer, right? It graduated, the hydrometer is graduated. I'm not sure, like, you can see the number. So you can read the market, the mark on the hydrometer. This is what I'm saying, not graduated. The hydrometer is marked like this. The marks on the hydrometer, this is what you are reading. So after reading, you can get the specific gravity. The hydrometer will give you the specific gravity. Then if you get the specific gravity, by using this table, let me go back, this previous slide. This one, you get the value of K, because you know already the temperature of during your test. So after getting the specific gravity from the hydrometer, then you will be able to obtain the value of K. Yeah. Then if you have the value of K, the T is just time. I just said, if you want the T, the time, you can use chronometer. You can use your watch to obtain that. This watch, as I explained previously. Okay. So if you have T now, what is remaining is just L. So the L also is depending on the reading of the hydrometer. So you can obtain the L. So after obtaining this L, so you can calculate the corresponding diameter of all this. This corresponding diameter, then you can say that this specific gravity you have measured, the soil, that mass, because if you say specific gravity, it means also mass. From that specific gravity, you can obtain the mass of the soil in suspension. You can say that this mass, the soil that has this mass, that soil has particles with diameter smaller than D, than the D you calculated. So you can, after knowing the mass of that part, you can divide with the total mass and obtain, by multiplying by 100, you can obtain the percentage of the soil smaller than this particular diameter D. Then after making both sieve analysis and hydrometer analysis, you can combine these two to make only one graph, like this one. So this circular point, this circle are for sieve analysis, and this triangle are from hydrometer analysis. Okay, so as you can see, sometimes we have some discontinuity. It happened every time. Discontinuity where these two curves overlap. So this discontinuity is because soil particles are generally irregular in shape, not same shape. And also the sieve analysis are giving intermediate dimension of particle. On the other hand, the hydrometer analysis gives diameter of equivalent sphere that will settle at the same rate as the soil particle. This is what making this discontinuity or discrepancy. Otherwise, we will have a smooth path like. So if you use to do this in the lab, you can know how to correct this, like to make it smoothly. Okay, so I think this is the end of this section. So we need one more video, to complete this chapter number 2. Yeah. Okay, thank you very much, and see you next time to finish the chapter.